Thank you, Aaron. Thank you for the organizers for inviting me and for organizing this workshop. Yeah, so as I said, so I'm going to be talking about how we resolve the optimal metric distortion conjecture. And this is joint work with Daniel Halpern and Nisarg Shah from the University of Toronto that will appear at Fox 2020, was recently accepted at Fox. And Daniel, if you haven't met him already, he's a brilliant undergraduate student. Well, I guess he was an undergraduate student up until a few months ago that will be advised by also brilliant Nisarg at the University of Toronto, and he will be joining Harvard University to work with Ariel this fall. So he already has a couple of papers as an undergraduate, so I expect to hear many great things in the future too. And Nisarg, I guess you already know, and we've been hearing a lot of great things from him. So yeah, so this paper has been a pleasure to work on, and another benefit that I have here is that Elliot did a lot of the work on kind of defining and motivating everything, but just for completeness, let me just define some of this setting. So we start off with this metric space. We have a metric space, and within this metric space, we have a set of voters, in this case, these blue vertices, 1, 2, 3, and 4. And we also have some candidates, A, B, and C. And our goal is to choose one of these candidates. So if we choose candidate B, then the cost, the social cost of that choice is going to be the sum of the distances in that metric space of all the voters from that candidate. So we just sum up all these distances, and that tells us how good that choice was. If instead we chose A, then we would pay the corresponding distances, and that will be the social cost. And within this, throughout this talk, our goal is going to be to minimize this objective, minimize the sum of the cost. And of course, if we knew all this information, if we knew exactly all these distances in the metric, it would be trivial to just check each one of them, compute their social cost, and output the one that has the minimal social cost. But of course, the point is that instead of having full access to this underlying information, these distances, well, all we know is for each voter, the ranking of the candidates from their perspective, shortest distance first. So each one of the voters tells us their preferences, which are the rankings. And our goal now is to design a voting rule that uses this compressed information, so this limited information regarding the actual distances, and using only this information to try to choose a winner. But nevertheless, our goal is going to be to evaluate the quality of this outcome based on the actual underlying distances. So although we have this compression, this lossy compression of information into these preferences, we try to still evaluate using worst case approximation factors with respect to the true underlying distances. So formally, we have a metric over n voters and m candidates with the distance function d. The distances satisfy a triangle inequality and induce this preference profile, which then our voting rule uses in order to, as input, in order to output the winning candidate. So the social cost is measured by the total distance from the voters. So like for candidate A, for instance, it will be the sum over all voters of the distances of these voters from the candidate. And then we evaluate the quality of a voting rule F using the measure of distortion, which is the worst case over all instances of the social cost that this of the output, the winner of the voting rule chooses over the optimal thing if we actually knew the underlying distances. So this is exactly the worst case approximation factor, but rather than computational constraints, what we have is information constraints in the numerator. And this is just a copy of the tables that also Elliot included earlier, summarizing some of the results in this literature. With the most relevant ones to this paper of ours being the last two. So the paper by Kamesh and his student Wang, who managed to go beyond the distortion of 5, by achieving this 4.2 and providing a new voting rule, and the lower bound of 3, which we know is the best. And by the way, throughout the talk, I'm going to be focusing on deterministic voting rules, although the paper does contains some results for randomized that I'm briefly going to mention at the very end. Right, so I mean, there's no spoiler alert here. I mean, you already know from the introduction what the result is. We managed to actually get the 3 and show that this bound is tight. But first, again, for completeness, let me quickly remind you what the simple lower bound argument is that requires just 2 candidates to show you that 3 is not going to be something we can surpass given this limited information. So the example that Elliot explained in detail. So we have half of the voters, just two candidates A and B, half the voters say they prefer A, half they prefer B. So without loss of generality, let's assume the rule selects A. You can, there's no way to distinguish between the two candidates. And the bad instance that arises there is if you have these two candidates A and B, half of the voters lie essentially in the middle, and they have like a small, arbitrarily small preference for A over B. So they prefer A, but only mildly so. Epsilon can be arbitrarily small. Whereas the other half of the voters are exactly really liking B. They would love to that this would be the outcome. And this would be the example that gives you a 3 lower bound that you cannot get better distortion than 3 for any deterministic mechanism. And it's one thing that one of the reasons I'm mentioning this is to point out that in this example, all of these, this crucially depends on half of the voters being indecisive. This means that somehow they're not really able, they don't have a strong preference for their first choice over the second one. They're more or less indifferent between the two, and that we're going to come back to this later on in a parameterization of our bounds that also depends on decisiveness, and see how we can circumvent this bound. And this is our result. So we actually get the 3, the optimal distortion bound. But in order to explain how we achieve this, I first have to define a family of bipartite graphs that we use and in order to choose the winner based on our plurality matching voting rule. So given a problem instance, for each candidate, we define a bipartite graph whose vertices on each side corresponds to the descent of voters. So we have voters on the left side of the bipartite graph, voters on the right side. And note, I think it's important to note that there's a different graph for each candidate. So given an instance, we have M different graphs, one for each candidate. The vertices are the same. It's still the set of voters on the left, set of voters on the right, but the set of edges will differ. The set of edges are going to depend on the candidate whose graph we're actually looking at. So in particular, each edge I, J, I on the left, J on the right, exists when in I's vote, on the left voter's vote, A weakly defeats the top choice of J. And you see that A comes in here. This is the part where it's the edges are specific to the candidate whose graph we're looking at. And we're saying that in the left guy's vote, the I's vote, A weakly defeats the top choice of the right voters. So if we look at all the preferences of the voters on the left and emphasize where A stands in this rankings, and look at all the preferences of the voters on the right and look at their top choice with red, right? So maybe the easiest way to parse this is to actually look at it from right to left. And for instance, let's look at voter 2, right? So what edges are incident on voter 2 on the right-hand side? So we first look at the top choice of this voter. So the top choice of this voter is candidate C. So he's connected, the edges that will appear according to this graph are going to be all the voters on the left that actually believe A weakly defeats C. So the first voter thinks so, the third voter thinks so, the third and the fourth voter thinks so. So in fact, just to verify, we look at where C stands in the rankings of the voters on the left and where A stands, and whenever A is greater or equal, so is weakly preferred over C, we create an edge. Okay, so that's when we have an edge on the right, and then we continue the same thing for the fourth voter on the right. We would see what edges and so on. So we get all the edges here. Clearly, one important thing to point out is that, of course, by the way, if we had a different candidate, this graph is for candidate A. Clearly, if I try to get the integral domination graph of candidate B, we have same vertices, but totally different edges, right? Because on the left, we'd be emphasizing B and therefore deciding what edges to include. So now the thing is that clearly, if you look at this graph, you can get the intuition that the more edges there are in this graph, the better the candidate looks. So right now we see there's a lot of edges here. So each edge indicates that someone thinks highly of A in some sense, right? So for example, just to give you an example to help with intuition here, if the graph is complete, that must mean that the candidate that we're looking at is actually the top choice for everyone. That means everybody thinks they're the best choice. On the other hand, if someone's the worst choice for everyone, there's going to be no edges if they're ranked at the bottom, right? And of course, there's things in between. And the summary, in a nutshell, what we do, the approach that we use for the voting rule is we're looking at these graphs. For each one of the candidates, we're going to be looking at these graphs, and we're trying to get one candidate whose graph is dense, right? In some sense, that I'm going to define formally in a bit, has a lot of edges, right? Somehow it covers, like many people think that this candidate is good. And again, one way to interpret this, if you need some intuition just to remember this, is for everyone on the left. For instance, when voter 2 on the right says, actually, I don't like A, I think C is my best option. The edges that he's connected to, his incident edges, point to people on the left, voters on the left, who disagree. So he thinks C is the best option. He might say, if we choose A, voter 2 here might complain and say, no, I like C more. Well, all his neighbors disagree, right? So the more edges you have, it's kind of more reasons to, in some sense, charge the fact that 2 is dissatisfied, but sure, 1, 3, and 4 are happier than, like giving 2 his best choice would have made 1, 3, and 4 worse off. And rather than just saying, when we talk about edge density, rather than just saying, I'll sum up the number of edges, I'll choose the candidate with whose graph has the most edges. Instead, what we want is, in some sense, a broad appeal. We want many different voters to like this candidate. And the way we capture this is by saying, we want for every voter on the right who's dissatisfied to exist a distinct voter on the left who is happier with the candidate we chose. And that might already suggest in your mind that what we're actually looking for is a matching. So essentially, we're saying for everyone that is unhappy on the right, there's someone distinct person on the left that is happier than if we chose the best choice of the person on the right. And this is it. Really, what our voting rule does is it looks at all the graphs. So it's easy to compile all of these graphs. For each candidate, we get the bipartite graph, and we check in polynomial time if it has a perfect matching. If it does, if it actually has a perfect matching, then we choose any one of the candidates whose graph has a perfect matching. And that is the description of the voting rule. So take all the graphs, generate for every candidate its integral domination graph, check which ones of those actually yield a perfect matching. There's enough edges and a wide enough support for this candidate that you can actually get a perfect matching. And if such a matching, and if you find some of these candidates that satisfy this, could be more than one, then choose any one of those, doesn't matter. And this will still guarantee you the distortion of 3. A natural question at this point, though, would be like, wait a minute, though. How do I know that such a candidate exists that would give me a perfect match? Maybe I try all of them and none of them give you a perfect matching. And that's, of course, the main technical lemma of our paper, the ranking. It's an implication of a more general lemma, the ranking-matching lemma, which shows that there always exists a candidate whose integral domination graph admits a perfect match. That means choose any instance you like, any number of voters, any number of candidates, any preferences you like. They're always going to exist. At least one of these bipartite graphs is going to admit a perfect matching. And therefore, our algorithm can in polynomial time find one of them and just output this. And that's the description. I cannot, this lemma does all the heavy lifting, and it's quite technical, so I cannot really summarize it here. But in a nutshell, it actually assumes that the instance, we start off by assuming that there exists some instance where no candidate has a perfect matching, and then we leverage Hull's condition to show that this leads to a contradiction. But the reason how we use this lemma is exactly to get this next theorem, is that any voting rule that always outputs a candidate that satisfies this, so that has a perfect matching, has distortion free. And one very nice thing about this is that actually, because the ranking-matching lemma does all the heavy lifting here and shows the existence of such a perfect matching, of such a candidate that admits a perfect matching, the proof for this theorem actually becomes really, really short. So this is really it. So we start off, we say, okay, so the social cost of A, we just write it out. What is the social cost of A? It's the sum of the distances. This is upper bounded. And that's the first time when we use the matching, the existence of the matching. We're saying The distance from I to A is less or equal than their distance from the top option of the person they're matched to. That's the definition of an edge existing there, right? So if there's an edge there, it means that I prefers A to the top option of their match. Then we use the triangle inequality. Then this is the second time where we use the matching. So we're summing over all these terms because it's a matching and there's a one like correspondence between I and top of I and top of MI. We just replace top of MI with top of I, triangle inequality again, and that's it. And we get the 3 distortions. So it's surprisingly short and just one block of inequalities, which we think is kind of appealing, especially given the fact that previous bounds often required a lot of work. Of course, I'm not saying this is an easy bound because a lot of the technical difficulty is just compressed into this this matching ranking lemma. But it's kind of nice, and I'm not expecting you to follow all these inequalities right away, but you can verify this offline, and neither one of them is going to be surprising. It's pretty straightforward. So this is what we think is pretty cool. It is worth noting that our approach was inspired by the really cool recent paper by Kamesh and his student Wang that talked about the matching uncovered set. So apart from the result that I mentioned before regarding the paper, where they get the 4.2 bound, this improvement in the distortion at roughly 4.2, they actually also paved the path. They suggested a sufficient condition for getting a distortion of 3. So it's a similar, they define similar bipartite graphs to ours, where voters are on the vertices, but for each pair of candidates, the difference is they have a different graph for each pair of candidates. Rather than having a bar graph for each candidate, now they have more graphs. They have, for each candidate A and candidate B, there's a different graph. And to accept, the sufficient condition was that there exists a candidate A such that for each one of A's graphs, there exists a matching, a perfect matching. So it's related in the following way. So they didn't manage actually to also show that such a candidate exists, but our solution answers this in the affirmative. So our proof also implies a positive answer for their question of such a candidate existing. In fact, rather than looking at different graphs and having a different matching for each graph, essentially what we're proving is there's one matching that covers all of these graphs that they define. So there doesn't need to be a distinct matching per graph. Okay, so we get the distortion of 3. This also implies this kind of closes this conjecture. But I argued that the ranking that our lemma is actually stronger than what it initially appears. So let me, at the risk of actually losing some of you, let me try to explain how much stronger our lemma is and maybe other implications that this might have. So first of all, this was our integral domination graph for a candidate A. Now, in fact, what we use for the ranking matching lemma is a PQ domination graph, where the vertices on the left are still the voters, but the vertices on the right are now the candidates, right? And an edge IX, now X is the candidate, exists when I's vote, when in I's vote, A weakly defeats candidate X, right? So that's actually easier to find these edges. You just look at which candidate A defeats in the voters' ranking, and you create those edges. So again, more edges imply that the candidate at hand, in this case, candidate A, is more appealing. But we also enhance this graph with 2 weight vectors. One on the left, the P vector for the vertices of the voters, and a Q vector for the vertices of the candidates. And we normalize these weights so that they add up to the same number. So what we actually show is that take any such graph, any instance, again, any voters, any candidates, and any weight vector normalized to add up to the same values, that you can always find a perfect fractional matching. And what do I mean by a perfect fractional matching? I mean that you can assign weights on the edges. So let's say here you could assign a half here, 0.2 here, and 0 here. And they add up to exactly the weight of the vertex on the right, 2.2. Right, so, sorry, that was wrong. So I should say 1, 1, 1, 1, and 2. And of course, that would mean that on the left, because the weight here is 1, this should be, if this is 1, this should be 0 and 0. So a perfect matching, a perfect fractional matching is an assignment of weights on the edges such that for every vertex, the sum of its incident edges weights is exactly equal to the weight of that vertex, right? So, you know, it doesn't necessarily, so at first sight, you listen to this as like, this is apples and oranges. You look at this graph, it doesn't look like the previous graph. It doesn't look like a more general statement. You know, there's weights, it doesn't, well, how are the two connected, right? So here's the connection. So the previous graph that we had voters on one side, voters on the other, and what we needed was the existence of a matching, a perfect matching like the one on red. So in reality, though, rather than caring about all the rankings of the voters on the right, all we cared about is their top choice, right? So what is their top choice? And in fact, we don't even care about their identity. If you look at this, voter 1 here and voter 3 here are identical with respect to the neighborhood because, you know, all that matters is their top choice. So we, in fact, we just replace these voters with the candidates that were their first choice. And now that looks a little bit more than like the other graph, because now on the right you have candidates. But there's multiplicity. You see candidate A twice. And of course, it's the same neighborhood, as I said. So we can merge these two. And I should say these slides are by Nisarg. I didn't do this work. I'm slightly editing his existing slides. And if there exists a graph in this, and you see that now, if I assign the weight here to be 2, the weight here to be 1, and the weight here to be 1, I've actually captured a perfect, this now corresponds to a perfect fractional matching, right? And if on the left, I assign all the weights to be 1, right? So in a matching in this graph, in fact, it's easy to verify that if matching in this graph exists if and only if a perfect fractional matching in this graph with these particular weights exists if and only if there existed a perfect perfect matching in the integral graph. So in other words, if we take our general lemma and replace on the left, set all the weights to be 1, and on the right, we set the weights to be proportional to the plurality score of each candidate, then that directly implies the integral matching that we got, which was the special case that we used in order to get our distortion bound. So in other words, if we choose all the weights equal on the right, left, and weights proportional to the plurality score on the right, we get the plurality matching. But this gives rise to the following interesting question. What if we try something else, right? What if instead of trying these weights on the right, we try, for instance, you know, and generates a multitude of different voting rules. You can come up with a weight that kind of signifies the importance of each candidate and importance of each voter and come up with a different voting rule. One interesting example that we observed is, what if in the right, we instead do equal weights rather than proportional for all the candidates? Instead of doing proportional to their plurality score, we do equal weights for all the voters and for all the candidates. So it's interesting that then we actually get a different voting rule. That's an orthogonal result with all the ones we were discussing before, where candidate A selected has the following guarantee, that in any X fraction of the votes, candidate A weakly defeats at least an X fraction of the candidates for any X. Choose whatever X you like, whatever portion you like, and this is satisfied. And Nisarg pointed out actually that this resembles this interesting open problem regarding the existence of solutions decor for committee selection. But in general, like we haven't really figured out the extent to which playing with Q and P, the two vectors, can give anything interesting or new interesting voting rules. So before I conclude, let me quickly discuss some refinements of the results that we have using the alpha decisiveness framework of Anshelevitz and Postel. So as I mentioned early on, when I showed you the lower bound of 3 for the distortion, I mentioned that it heavily depended on the fact that half of the voters were indecisive. They didn't really have a strong preference between the two candidates. And in fact, this framework essentially parameterizes this and says, you know what, let's consider instances where each voter I, for each voter I, if B is her top choice, then the distance for B is less or equal to alpha times her distance from any other candidate C, where alpha, you know, is less or equal to 1. So for instance, if alpha is smaller than 1, that implies that you have you're more decisive, you have a stronger preference for your top choice. And there's several interesting cases for this. For instance, for alpha equals 1, first of all, this just captures the standard case. That's the essentially not restricting the metric in any way. For the alpha equals 0 case, then it means that the voter's distance from, so the voter's distance is located, the voter is located at her top choice. There's zero distance for the top choice. And that captures as a special case the peer selection problem, where the voters are the candidates. And you assume that every voter thinks of themselves, they totally agree with themselves. So they have zero distance from themselves. So it's already an interesting and studied problem that is captured by the alpha equals 0 case. So our results, the same block of inequalities, just slightly updated, implies a bound of 2 plus alpha. You can see again that for alpha equals 1, you get 3, the result we already know. And for alpha equals 0, though, you actually get a 2. So for the peer selection problem, we get an improved distortion. So that lower bound we show, if you do not have this indecisiveness, in fact, you have strong decisiveness, you get a better distortion, you get a distortion of 2. And it's worth noting that although some of the other results are connected to this matching uncovered set by Kamesh's and Wang's paper, that actually, without the additional strength of the ranking-matching lemma, you wouldn't be able to achieve this bound. So the best you could get using that more relaxed definition would be a 2.5 plus alpha over 2. So even for alpha equals 0, that would give you just a 2.5. That's a lower bound distortion. And we also have a lower bound that any deterministic voting rule has distortion at least 2 plus alpha minus 2 over m, m being the number of candidates. So at least if the number of candidates is really large, so if you don't restrict the number of candidates in arbitrary instances, this is actually as good as it gets. Okay, so last slide. Apart from the results that I mentioned, we also improved the best known bounds for randomized rules. Again, with or without alpha, we have some different parameterizations. However, as Elliot mentioned, the optimal distortion of randomized rules is still open, so we don't know what it is. It's somewhere between 2 and 3. That's one of the compelling open questions here. And it's worth studying different extensions of the problem that we're considering. For instance, if you have weak preference orders or this committee selection, committee of K candidates rather than just one, and the connection that Nisar pointed out about the core for the committee selection. But of course, this is already covered by all the stuff that Elliot mentioned about all these distortion framework extensions where you can study other than just choosing one candidate, choosing the selection, matching, clustering kind of problems, and all of these settings where we can improve and maybe see if we can apply some of the intuition from this lemma. And that's it. Thank you very much.